All right, hi everybody. Welcome back. This little video we want to go through a really important topic, really useful topic when you're just getting started running regressions, is nonlinear transformations in an otherwise simple OLS setting, right? So this goes for being a consumer of econometric output, right? You're reading papers, you see people using log transformations and square transformations. We want to know, what is the motivation there? What features of the data suggest that those transformations would be helpful? And we'll look at how to execute the transformations in Stata, and then how to interpret the output. All right, so nonlinear models, let's go. What we need is some data to work on. And in this case, we're going to call up an example data set from Jeffrey Wooldridge's Econometrics textbook. And he's put through Boston College all of the data sets that he uses in his textbook available online. And even better than that, there's a little do file that's been written that can call those files up directly. So if you recall the Federal Reserve Economic Database, right, we have the FRED use command. So as long as you know the variables, you can bring those in right into Stata. Well, Boston College, they've written something similar with this BC use command. And of course, that has to be installed into your Stata. It's not part of the default package. So what you're going to want to do, if you want to play along here, is you'll type in ssc install bc use, and then hit enter. I've already installed it. So it's going to tell me that I already have everything up to date. So I'm all good to go. And the data file we're going to play around with here is going to be a wage data file. So our variables of interest here are going to be hourly wage, I believe, for non-skilled workers. And we're going to just run a simple return to education model. So I believe our data file name here is going to be wage 1. So we can type in BCU's wage 1. And look at that. We now have a data file ready to go with a lot of interesting variables here, the majority of which we are not going to look at for the purposes of our little example here. So we're thinking, okay, what's the return to education? What's the expected change in someone's wage due to a 1-year increase in education? So we're not going to talk about how to properly specify this model. That's for another topic. But just imagine that we're running a simple regression of the level of wage as a function of the level of education. And here we've got our 526 observations. We've got an R squared here of about 16.5%, as we're patiently waiting for my Stata to show us the rest of the results. And here we go. So, all right, we have a coefficient there on education of 0.54, a t-stat of over 10, so highly significant, beyond 99% confidence. And so everything looks more or less like what you'd expect, right? So we have, for each year of education, we're adding on average 54 cents to the individual's hourly wage. So, again, nothing from this regression output makes us suspect anything in terms of non-linear relationships. So we need to know kind of where to look before we're satisfied with this result. Right? So kind of the obvious thing to do is once again just give your data the eyeball test, right? Just call up a simple two-way scatter plot, right? So you can do this in the graphics drop-down menu here, but just using the command two-way scatter, and then we'll put in our y variable, in this case wage, and our x variable here, education. And all we're looking for here is any kind of indication of nonlinearity. And obviously nothing definitive here, but if we wanted to draw on our graph here, we can go up to Start Graph Editor, do Control L, and we can draw some lines here, and we can kind of see what's happening, right? So the relationship between education and wage starts out relatively flat, which is not surprising, right? So we're looking at education here up through grade 12. And if you only have 5 or 6 or 7 years of education, we don't expect to see big jumps in your wage level. You should stay in school. What are you doing, right? But once you get about at a mean level of about 11 or 12 years of education, then we really see that impact take off, right? That marginal effect seems to be increasing if we're just kind of eyeballing the best fit line here. And that's obviously an indication of a non-linearity or even a structural break here, right? So we're getting steeper and steeper and steeper. The marginal effect of education seems to be increasing as the level of education increases. Okay, so that's definitely one thing that we're going to want to keep in mind, just the visual of it. Another great way to check whether or not there are indications of nonlinearity, and this again is maybe not obvious, but it's to look at the underlying coefficient of skew for the distribution of your x and y variable. And again, we can do this kind of with the visual eyeball test, right? We can just call up the frequency histogram. And so if we call up the histogram for wage, so in Stata, it's just HIST wage, we can change the options, the number of bins, etc., and how we're measuring the frequency. But we're just doing the visual here, so we can just do the default. And in terms of symmetry or skew, right, we can easily see that we have a right-hand or positive skew to this distribution, right? We have an elongated right-hand tail of the distribution, a lot more variability above the mean than below the mean, right? And then we have this truncated left-hand tail. And of course, that's by definition of our variable here, since it's hourly wage. You're never going to see values below 0. We obviously shouldn't see values below the minimum wage. But there's a very limited amount of variability that, by definition, can happen below the mean, but there's no upper limit on wage, so we get that elongated right-hand tail. So keep that at the back of our mind. We have positive skew for our y variable, wage, and let's do the same thing for our x variable here, education. Call up that histogram, and here we can see, maybe not quite so dramatically, but a left-hand or negative skew. So in this case, technically you're not supposed to, but people can drop out of school at any point, right? Once you start that first year. Most people make it to year 12, right? And then there's kind of limited variability above the mean, right? Once you kind of get through college and graduate school, you're pretty much done, right? But that left-hand tail has that elongation. The right-hand tail is going to be somewhat truncated. So again, visually, we seem to see some left-hand or negative skew. We're going to want to verify that in Stata by simply calling up that third moment of the sample distribution, the coefficient of skew. And we can do that with the tabstat command. So we go tabstat, and then we list out our variables, wage and education, comma, stats sk. Right? So you can kind of tailor that tabstat command to call up specific sample statistics. In this case, that sk is our third moment, or our coefficient of skew. And look at that, the eyeball test was right once again. Our coefficient of skew for wage here is 2.0. Coefficient of skew for education is negative 0.61. Right? So if you look into it a little more, right, if we had a perfectly symmetric, say a normal bell curve distribution, that coefficient of skew is going to be 0. Right? Equal amounts of distribution above and below the mean, they would just cancel each other out. So that positive value for wage, greater variability above the mean, negative value for education, that elongated left-hand tail, greater variability below the mean. Okay, so now, what does this have to do with linearity? Great question. Let's go back to that visual of our scatter plot, right, between our y and our x variable. And let's kind of link this together with that idea of negative versus positive skew. So let's do the same thing that we did before. Let's go to that graph editor, Control L, and we can draw right on top of this. Right? So remember what that meant for education. Right? We had that elongated left-hand tail. So once we get up to that mean, right, below that point, we have this wide variability. Then above the mean, that variability is somewhat more truncated. Right? With wage, it had that positive skew, right? The variability below the mean, right about here, right, is going to be somewhat truncated. Above the mean is going to be a greater level of dispersion. So see what we've done here. We've basically boxed in the most likely points for these observations in the tails of the distributions, right? That combination of a short tail in one variable and a long tail in the other is going to place those observations within these boxes. Right? So short tail on the y variable, long tail below the mean for our x variable. What do we see? We see this elongated box that's going to give us, by definition, a pretty flat slope, if not zero slope, right? And then in the right-hand tails, right, we have a truncated right-hand tail for the x variable, education, and the elongated right-hand tail for y variable, wage, and that's naturally going to, again, place those observations within that box, and it's going to increase the slope, increase that marginal effect. So, how can we linearize this relationship? Well, if we had a version of our x and y variables that were more symmetric, right, the relationship between them would be more linear. That's where those transformations come in. Right? So remember we talked about those most common transformations that you see, right? We just kind of threw it out there. You see a log transformation here, a square transformation here. Well, here is the motivation. Right? And it turns out if we apply a natural log, so log base e, transformation for our y variable in this case that has positive skew, the transformed version is going to be more symmetric. Its sample distribution is going to be more symmetric. So we're going to need to generate that variable. It turns out in this data set, this Wooldridge example data set, there's already a variable here called L wage that is the natural log of wage. But imagine that wasn't there for the moment. Let's go ahead and actually just get rid of that. So we can create it ourselves, right? Which is normally the case when you have raw data. You have to create all of your transformations, right? But we can do it simply with a generate statement, and we won't be too creative here. We'll just call it L wage again. So L wage is going to be our log, so it's going to be log, and then parentheses the name of the variable that we are transforming. So the default log transformation is that base E in Stata. If you wanted to do a base 10 log transformation, you would have to adjust that command. That's very rarely done, right? So we'll go ahead and hit enter there. And now we've got two versions of our wage variable. And if we kind of put those side by side, literally a two-way scatter plot once again. So let's go back to our command, two-way scatter. Now instead of x and y, it's going to be log y, L wage, versus its original version, wage. And of course, this is going to look like what you see in your math textbooks, right? A log transformation relationship. But see what this is doing, right? Think about the variability here on the right-hand side, say our wage varying from 15 to 10, right? Well, the variability in our new version of wage on the y-axis here, right, is going to be between, say, 2.7 and 3.2. It's shrinking that dispersion of large values, right? Decreasing that dispersion, truncating the right-hand tail of this distribution, which is exactly what we want to make it more symmetric. So let's go back to that tabstat command where we called up our coefficients of skew, but now instead of putting wage and education on, let's put wage and its log, wage and L wage, and that's exactly what we see. So the raw data had that heavy positive skew at 2.0, our transformed version, much closer to zero, much more symmetric, a skew of 0.39. Okay. So the suggestion here is to use that transformed version of our variable, decreasing that nonlinear nature of the relationship. Let's think about what we need to do for that education variable that had negative skew. Well, here we need to elongate the right-hand tail. We need to increase the dispersion of the right-hand tail, and it turns out a polynomial, a square transformation, is going to do just that. So same thing, we need to generate a new version of the variables. This is education squared, so call it whatever you want. EDUC SQ, or just EDUC2. Creativity is not my strong suit, but we'll know what that means. And then we'll call up education to the second power, so the little caret 2. So there's our new variable, and it's going to show up in our data set here, right alongside our new version of wage. And just to get the feel for what this transformation does, let's call up that scatter plot yet again, and here we'll put the squared version related to, for each observation, related to its linear version at the level of education. Right? And again, we all know what this is going to look like, so it's going to have that increasing slope, that y equal to x squared kind of functional form here. So again, think about what we're doing now. So again, just to pick kind of points that are easy to see. When education ranges from 15 to 20, well, our new version, education squared, is going to range from about 200 to 300. Right? So the variability, the dispersion of those observations is increasing, elongating that truncated right-hand tail, making the result more symmetric. The last kind of visual that we'll want to look at here before we finally get to running the regression is yet again calling up another scatter plot, but this will be the y-x relationship again. So wage and education, but it's not the original versions we want. It's log wage versus education squared. Let's see if we can see the difference here. And we certainly do see a difference. So let's go back to the graph editor. I like to draw in my graphs, right? So now, because the dispersion in the two tails, the left and the right tails of both the x and the y variables, are more or less equal, right, or equalized relative to what we had before, we don't see that obvious change in slope as our x variable here, education squared, increases, right? In other words, the dimensions of the boxes are going to be more or less equal above and below the mean. What was that? Sorry. That's supposed to be a straight line. I get excited when I run regressions. I lose control. So, again, that's the visual of it. We're not doing any mathematical proof, but that's a really good way to think about the motivating factor for these transformations. So, let's finally get to the regression we're going to want to run now. Remember, initially we had wage as a function of education. Well, now we just change wage to its log. And then instead of just changing education to its square term, it's going to be much more useful to have both the level and the square, right? We'll kind of look at the equation that results from this, but that way we can account for a lot of different functional forms, increasing returns, diminishing returns, primarily. And in Stata, right, obviously we could just type in our new variable here, educ2, that is the square, but it's nice to know kind of a shortcut here. If you didn't really want to include that new version of your variable in your data set, you can use what we can call the Stata interaction operator. It's basically just creating the product of two variables, right? And the two variables that are going to need to be multiplied here are education and itself. So the product or interaction operator is the hashtag sign or the pound sign. So we're going to do education pound hashtag education. But we need to do one more thing, because that operator was originally intended to be used for factor non-continuous variables. We need to tell Stata that these are continuous variables. So the Stata speak for that is C dot as a prefix for your variable name, and we're going to want to do that for both. So when we get into dummy variables and factor variables, we don't have to do that. That'll be a lesson a little ways down the road. But for now, this is going to be equivalent to our education squared, right? So again, you don't have to do it this way, but it's nice to know that you can. And we hit enter here. So now, what do we see? Well, now, of course, we have two coefficient estimates that are indicating the relationship between education and wage. So we have to do a little bit of thinking before we can, really interpret those numbers. But before we get there, right, we can notice right off the bat that we do have almost 5% significance here for the level of education, and 1% significance for education squared. So the model seems to be improved just on that basis by adding that second variable. We have to be careful comparing R-squareds or even adjusted R-squareds across models, because we do have a different dependent variable here. But all signs indicate that this is an improvement. So the last step now is interpreting the results. So again, for me, not the brightest bulb, I like to write out all my equations, right, before I can really start to interpret it. So what this is going to look like, right? Our estimated regression equation here, so these are roughly the coefficients that we saw, our intercept, that negative 0.067 coefficient on the level of education, positive 0.006 coefficient on education squared. Well, to really get the meaning of that, right, we have to take the derivative, right, taking the partial derivative. But remember, and again, this is another lesson, that when we have that log transformation here, it's going to give us an elasticity interpretation. So this is going to be measuring the unit change in x associated with a given percent change in y, in this case, education. So, but really we're just taking the derivative of the right-hand side here. So we have the kind of the baseline marginal effect, this negative 0.067, and then got to take the derivative, so we get our 2, right, times our coefficient on education, the 0.064 technically, right? And we just multiply that out, and now we get this marginal effect. And it's exactly what we wanted, right? We wanted to show that the impact of education increases as the level of education increases, right? So every extra year you stay in school, particularly beyond the mean, is going to have not only an increase in wage, but a wage increasing at an increasing rate. So let's go ahead and, let's go back to Stata here. Just to take a look at that resulting regression equation, let's go ahead and use the predict command here. So post-estimation, let's predict the fitted value, right? So call it L wage hat, right? And let's go ahead and plot that out. So one more time, call up that two-way scatter, but now instead of y and x, it's going to be y hat, right? So our fitted value versus education. And somewhat overly dramatic the way this is scaled, but we see what that data initially indicated, right? Certainly a nonlinear relationship. This is what we estimated. It really seems to be the best fit to those observations that we saw, right? So we see that initially that line is relatively flat, in this case actually estimated to be decreasing. Once you get past high school, then that wage effect really takes off, and it keeps getting steeper and steeper. That marginal effect keeps increasing as education increases. So, obviously this is just one example. It's not always going to be as clear-cut, but this is a great thing to add to your toolkit, right? Every time you're given a set of variables and a regression to run, take a look at those coefficients of skew, take a look at those eyeball tests, look at the histograms, look at the scatter plots, look for indications of nonlinearity, include them in your regression, and then just be cautious, take your time in interpreting the results, okay? So go ahead and leave a comment if you have any questions on this material, or if you have any suggestions for topics that you want to take a look at later on. I'll be happy to get back to you. Thanks a lot.